Hello, I am Professor Rathod. Now I am going to present on Stirling and Joule's cycles. Now basically what is cycles or what is a thermodynamic cycle? A thermodynamic cycle or a cyclic process consists of a series of thermodynamic operations also called as processes which takes place in a certain order and initial condition are restored at the end of the processes. When the operations or processes of cycle are plotted on PV and TS diagrams, they form a closed figure, each operation being represented by its own curve. The study of various thermodynamic cycles are very essential for the power development. These engines used the mixture for the different cycles, different mixture has been used. So cycle always contains you can see the turbine, the compressor, the heat exchanger and the heat combustion. So which one is applied to the Stirling and Joule cycle? Stirling cycle is one of air power cycle. It means this cycle operates on the strength of air. The Stirling cycle was introduced by Robert Stirling over the improvement of ideal Otto and diesel cycles. The Stirling cycle is a thermodynamic cycle that describes the general class of Stirling device. Stirling cycle consists of two isothermal and two isochoric. Isothermal means constant temperature process and isochoric means constant volume processes. The PV and TS diagrams of Stirling cycle has been given below. You can see the PV diagram, how it starts from 1 to 2, 2 to 3, 3 to 4. The process, if we look at the PV diagram of the Stirling cycle, 1 to 2 it represents isothermal expansion. Then the 3 to 4 it represents isothermal compression, and 2 to 3 and 4 to 1 those represents constant volume processes or constant volume operations. Now in this cycle which consists of two isothermal processes and two constant volume processes, it means two isochoric processes. In this cycle the four processes means there are four processes. The first stage represents isothermal expansion. In this the air expand isothermally at a constant temperature from V1 to V2. It means in this process isothermal expansion, heat supplied is equal to work done during the isothermal expansion. Therefore we can represent Qs is equal to process Q1 to 2, that is we can represent P1 V1 log to the base E V2 upon V1. It means MRT1 log to the base E V2 upon V1 is given as the standard equation 2.3 MRT1 log R, where R is the expansion ratio which we can represent V2 upon V1. The second stage or the second process, that is constant volume cooling process. In this process the air now passes through the regenerator and is cooled at the constant volume to temperature T3. Therefore in this process heat rejected to the regenerator, that is Q2 to 3 is equal to mCV T2 minus T1. M is the mass, CV is the specific heat at constant volume, because process is constant volume cooling process, and T2 higher temperature minus lower temperature. Then the next we can see one of the third stage, that is isothermal compression process 3 to 4, the air is now compressed isentropically at a constant temperature T3 in the engine cylinder from V3 to V4. So in this process, heat rejected by the air is happens. It means we can write Q suffix R is equal to Q process 3 to 4. We can the standard equation we have, that is P3 V3 log to the base E V3 upon V4. It means PV is nothing but MRT log to the base E V3 upon V4. Therefore the standard equation can be written as 2.3 MRT3 log R. In this process, R is the compression ratio that we can write V3 upon V4. And one of the next process, that is process 4 to 1, that is constant volume heating process. Air is heated at a constant volume to temperature T1 by passing it through the regenerator in the reverse direction to that of the process 2 to 3. So in this process, heat absorbed by the air, therefore we can write Q 4 to 1 is equal to heat taken from the regenerator. The equation is mCv T1 minus T4. As I told you, m is mass, Cv is the specific heat at constant volume, higher temperature minus lower temperature. Therefore work done, we know that is heat supplied minus heat rejected. Therefore we can write the equation. So equation we can able to get 2.3 mR log T1 minus T3. Therefore what is our interest? How to find the efficiency of that cycle? Efficiency is given by work done divided by heat supplied. As we have calculated, work done is nothing but 2.3 mR log to the log R T1 minus T3 divided by 2.3 mR T1 log R. Therefore this can be T1 minus, what it remains is T1 minus T3 divided by T1, or we can write 1 minus T3 upon T1. So T1 is the higher temperature, T3 is the lower temperature. So in these processes, the last two processes are performed with help of regenerator to make this cycle reversible. Now let us now consider, we have considered the 4 stages of the cycle. Now let the engine contain m kg of air, that is nothing but, also called as air is nothing but gas. That is why it's called as, the cycles are called as gas power cycles, also called as air power cycles, and its original position at a point 1. Therefore the process 1 to 2 isothermal expansion, process 2 to 3 constant volume cooling, process 3 to 4 third stage, that is isothermal compression process, stage 4, process 4 to 1, that is constant volume heating. Therefore we have seen that efficiency, that is nothing but higher temperature minus lower temperature divided by higher temperature. Now the Stirling cycle, as I was explained, process 1 to 2, process 2 to 3, process 3 to 4, and process 4 to 1, as I have explained. Now the efficiency also I have been stated. The thermal efficiency of the Stirling cycle is given by thermal efficiency, that is, as I told, higher temperature minus lower temperature divided by higher temperature. We can write it as 1 minus TL divided by TH, where TH or T1 I have taken before, that is higher temperature, TL, that is T3, that is we can able to take, that is lower temperature, though this is the efficiency. Now some of the applications we can able to see the Stirling engine in the diagram, then alpha Stirling engine. So these are the different Stirling cycles. One is application of the Stirling cycle. So this is whole about the Stirling cycle. There is one note for here, the Stirling cycle. The efficiency of the Stirling cycle is same as that of Carnot cycle, and all reversible cycle have same efficiency. So now one more note, if the efficiency of the regenerator heat taken from the regenerator during the process 4 to 1, the formula may be somewhat little bit changed. So this is all about the Stirling cycle, which was the first cycle. Now one of the numerical I have selected for the better understanding of the student, numerical I'll read, I'll show the numerical to you. An air engine working on the Stirling engine has a lower limit of temperature as a 400. The maximum and minimum pressure limits are 12 bar and 2 bar. If the expansion ratio of the cycle is 3, find its ideal efficiency. Then the solution, what it is given, we can able to represent this given data, that what we have given is T3 is nothing but T4, that is 400 must be converted into degree kelvins. It means 400 plus 273 is equal to 673. So P1, that is 12 bar, is given. Then what it is given is expansion ratio. It means as per the PV diagram I have represented the Stirling cycle on a PV and TS diagram. You can able to see over here. So V2 upon V1 is nothing but V3 upon V4, that it is given is 3. Now we know isothermal expansion process, that is process 1 to 2. If we consider it from PV diagram, then P1 V1 is equal to P2 V2, or P2 we have to calculate, then formula will become P1 V1 divided by V2. By putting the values we can able to get P2 is 4 bar. You can able to see in this that is the value is 4. Now similarly the isothermal compression process, that is process 3 to 4, that is we know P3 V3 is equal to P4 V4. Therefore we can calculate P4, that P4 after putting the values we can able to get the value of P4 is 6 bar. Now since air is heated at a constant volume in process 4 to 1, we have the formula as per the basics. T1 divided by T4 is equal to P1 divided by P4. So from this concept, as we have having the T4 is given, T4 is nothing but T3. So we can able to calculate the T1 after putting the values of P1 and P4, the values that is given. So we have the temperature 1, that is higher temperature we can able to get, that is 1346 K. Therefore by using the efficiency of the Stirling cycle, that is efficiency is equal to 1 minus T3 upon T1, or it may be T1 minus T3 divided by T1. After putting the value we can able to get the answer is 0.50. It means efficiency is 50%. So this is one of the numerical I have taken for the sake of simplicity of the student. Now Braton cycle, as I told you, the cycle this Braton cycle is also called as Joule cycle, also called as Braton cycle, also called as Joule-Braton cycle. So what are the main elements in this cycle? You can able to see the compressor, the turbine, the combustion chamber. So any cycle which starts from the initial and ends at the initial stage only. So Joule cycle, I have shown one of the idealized Braton or the Joule cycle. The compressor and turbine are coupled with the same shaft. In between the compressor and turbine, if the fuel, any type of fuel is supplied to the combustion chamber, combustible material, that is hot gases which falls on the blades of turbine, so the turbine rotates. Once turbine is rotates, the compressor initially the compressor starts with any of the type of the motor, but if the turbine starts giving its power, then compressor runs on the strength of the turbine. So we can represent it on PV and TS diagram, that you can able to see a Joule cycle consists of two constant pressure, that is isobaric processes, and two reversible adiabatic, that is isentropic processes, that we can able to see in this diagram, or in this we can able to see the Braton cycle. Will go for the next slide, the stages of the Joules or the Braton cycle as per the diagram I have selected. The first stage, isentropic compression, or isentropic are also called as adiabatic process. The stage 2, that is 2 to 3, constant pressure heating. Then stage 3, that is isentropic expansion, and stage 4, that is 4 to 1, constant pressure cooling cycle. So this is the open cycle and the closed cycle. You can able to see what is open cycle. when air is taken from the atmosphere which compresses inside the compressor, then it goes to the combustion chamber. After supplying the fuel, combustible material produces, then on the strength of that hot gases the turbine works. When the exhaust are exhausting to the atmosphere and not going back to the compressor with help of the heat exchanger, that is open cycle. But what is closed cycle? So when the exhaust from the turbine which again goes back to the compressor with help of heat exchanger, so that is nothing but the closed cycle. When you represent it on PV and TS diagram, it shall be formed like a closed cycle. The open gas turbine cycle can be modeled as a closed cycle by utilizing the air standard assumptions. Here the compression and expansion processes remain the same, but a constant pressure heating rejection process to the ambient, that is atmospheric air, replaces the combustion process. Next, now the TS and the PV diagram from 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So 1 to 2, in between 1 to 2 there is compression. 2 to 3 combustion is happening. 3 to 4 there is a turbine. It means the expansion is happening on the turbine. By that time the entropy remains constant. If we look at the TS diagram, 1 to 2, when the pressure or the temperature increases, by that time the compression is happen inside the compression. So that is the importance of the TS and PV diagram. So the next, heat added and heat rejected. When the heat is added, when after the isentropic compression, when the combustible material goes fuel is supplied in the combustion, that is heat is added. So in between 2 to 3 the combustion chamber is there. It means the equation taken in terms of the enthalpy, that is H3 minus H2. So by the standard it can be written as mCp, higher temperature minus lower temperature, that means Cp T3 minus T2 if the mass is considered as 1 kg of air, and Q out, that is when we consider the last process, that is process 4 to 1. So the higher enthalpy minus lower enthalpy, it means H4 minus H1, that is given mCp, higher temperature minus lower temperature. If the mass is unit, it means that is Cp T4 minus T1. It means specific heat at constant pressure, higher temperature minus lower temperature. Then the important is efficiency of Joule-Braton cycle. It is given, that is net work output divided by heat supplied, that is W net divided by Q in, or 1 minus Q out divided by Q in, that shall be written as 1 minus Cp T3 minus T2 divided by Cp T4 minus T1. So in this way the final efficiency we can able to write it as 1 minus 1 upon Rp raised to gamma minus 1 upon gamma, or gamma is nothing but K. K or gamma is nothing but adiabatic or the isentropic index. So value for the standard is taken 1.4. So if we didn't consider the denominator, so that can be 1 minus 1 upon Rp raised to gamma minus 1. Rp, as we have discussed, that is compression or the expansion ratio. Then one of the numerical I have selected for the students. So one of the numerical I have selected the numerical on the Joules or Braton cycle. I can read the numerical first. An air motor works on Joules cycle between 5 bar and 1 bar. The temperature at the beginning of isentropic expansion is 773 K and at the beginning of isentropic compression is 293 K. Determine the work done per kg of air and ideal efficiency. Here assume Cp, that is specific heat at constant pressure, that is 1 kilojoules per kg, and gamma, that is nothing but in the expression, in the equation of efficiency we have taken it K, that is nothing but gamma, or K is nothing but adiabatic or isentropic index, that is always 1.4. If I represent the given numerical on PV and TS diagram, we can able to see what it is given. Given is P1 is nothing but P2, that is 5 bar, and P3 is nothing but P4, as we can able to see on the PV and TS diagram. You can able to understand, that is 1 bar. Now the first thing I have to calculate work done per kg of air. So if we consider the process 2 to 3, that is isentropic expansion, we have the relation T3 upon T2 divided by P3 upon P2 raised to gamma minus 1 upon gamma. So after putting the value of P3 and P2, we can able to get the ratio of T3 upon T2 is equal to 0.6311. So I have to calculate the value of T3, as T2 is given. T2 is 773 and T4 is 293. After putting the value of T2, we have having the value of T3 is 488 Kelvin. Similarly, if we consider the process 4 to 1 on the PV diagram, 4 to 1 on the PV diagram, we have the relation T4 upon T1 is equal to P4 upon P1 raised to gamma minus 1 upon gamma. So after putting the value of pressures, we can able to get the value of ratio of T4 to T1, that is 0.6311. Therefore after putting the value of T4, I can able to find out T1, that is 464 K. Now we know heat supplied for this Joule-Braton cycle, that is MCP, higher minus lower temperature. Value of M is 1, Cp is 1, it is given. After putting the values, I can able to get the heat supplied is 309 kilojoules, and heat rejected is equal to MCP T3 minus T4. After putting the values, we can able to get heat rejected is 195. Therefore I have to write the equation of work done. Work done is equal to, we know, that is Qs minus Qr. After putting the value of heat supplied and heat rejected, we have the answer 114 kilojoules. And the second thing I have to calculate ideal efficiency, that is we know work output divided by heat supplied. Work output we have, that is 114 divided by heat supplied. Heat supplied 114 divided by 309 is equal to 0.369. Therefore the answer is 36.9 percentage. So dear friend, in this I have taken the separate bit or separate presentation on Stirling cycle as well as the Joule-Braton cycle. These are the air power cycles, the cycle which operates on the strength of air or gas. Therefore it is called as gas power cycles. So for the sake of simplicity of better understanding of the students, I have considered one of the example for each of for both of the processes. So this is all about the Stirling and Joule-Braton cycle. Thank you. Thanks for watching. Thank you.